This is the last new topic that we are going to learn before we start reviewing for the AP test. There's an entire unit 4 for this class, and we'll get to some of it after the AP test, but this is the last kind of topic that will be on your AP exam come May 13th. So, a couple things that we need to talk about in regards to polar functions. Just like we studied with other functions, all functions can have an average rate of change. Now, it's not necessarily a slope because these aren't straight lines, but we can talk about the rate of change for polar functions. That's what we're going to describe in the graph. Given that a polar function r equal to f of theta, we know that the radius r represents the signed radius of the function. We're calling it the signed radius because the radius can be positive or a negative value. We know distance is always positive, but we can have a negative radius showing that we flipped it across the graph. As we trace the graph of a polar function, we are interested in whether the graph of r equal to f of theta is getting closer to the origin or further away on a particular interval. Not the 4 colors, you're going to use the color code, but the extra color highlighter you have today, I want you to highlight the phrase getting closer to the origin or getting further from the origin. That is what we're going to be discussing today when it comes to describing these graphs, is whether the function, the graph, is getting closer to the origin or further away from the origin. Okay, I'm actually going to wait on this. We're going to come down here for a second. These two graphs, the one that's graphed polarly and the one that's graphed here in a rectangular fashion, are the same function. One is rectangular, one is polar. And so what I want us to do in actual example 1, before we even discuss what's above this, is highlight not concavity. We're not talking about concavity here. We are going to be discussing when the graph is getting further away from the x-axis or closer to the x-axis. So what I want us to do is take your first highlighter color, and I want you to highlight this graph from 0 to pi over 2. The way you would describe this section of the graph is that the outputs are positive because it's above 0. And it's getting bigger. So it's positive and it's increasing. I'm not talking about concavity here. I'm just talking about the function itself. It's above the x-axis and it's going up. So it's positive and it's increasing. That's this first section right here. Positive and increasing. Okay, there's going to end up, just preview, there's going to be 2 intervals here. But the first interval we're talking about for this graph is between 0 and pi over 2. Make sure you leave yourself room because there's actually a second interval for this graph, but we'll get to it. If we look at the next interval, and remember, I'm not talking about concavity, so not concave up, not concave down this time, but this whole next interval right here, from the maximum all the way to the 0, so past the midline, past the point of inflection, all the way to 0, that part of the graph is above the x-axis, so it is positive, but since it's going downhill, it is decreasing. So the function itself is positive, the outputs are positive, but the function is decreasing. It's getting closer to 0. This interval is between pi over 2 and 7 pi over 6. I'm reading those just straight off the graph, right? I started coloring blue at the x value of pi over 2 and finished at 7 pi over 6. The next itty-bitty bit in the graph is between 7 pi over 6 and 3 pi over 2. We have this section right here where it's underneath the x-axis, so it's a negative part of the graph. The outputs are negative. And it's getting smaller. So watch where I'm highlighting because it's not the next thing in the table. We're talking about where it's negative and getting smaller. Negative and decreasing, going down. This is the interval from 7 pi over 6 to 3 pi over 2. We have another itty-bitty interval where the graph is underneath the x-axis but is getting bigger, which means this section right here is the section where the graph is negative underneath the x-axis, but it's increasing because it's going up. This is the interval from 3 pi over 2 all the way to 11 pi over 6. what color, I probably previewed it to you earlier, what color do you think I'm going to color this itty bitty section right here? Red, because it's above the x-axis and it's positive, and it's increasing. So this little bitty bit right here goes back to the red section, which means we have a second interval we're going to attach on here, which is from 11 pi over 6 to 2 pi. Rectangularly, this makes a lot of sense to us. The idea of whether the function is positive or negative and whether it's increasing or decreasing. Since the rectangular versions of these trig functions immediately correlate back up to the polar functions, knowing how to graph a rectangular trig function will help you answer questions about the polar. So what we're going to do is, using the same color scheme, they're not in the same order, but using the same color scheme, I want you to take your colors for positive and increasing and highlight those same words here on the polar graph. Now that's going to be in the same angle sections that we set as our interval, which is from 0 to pi over 2. 0 is the positive x-axis, pi over 2 is the positive y-axis. And from 11 pi over 6 to 2 pi. We're going to hold on to that one because it's not going to make sense what I'm doing just quite yet. The next color that we're going to use is negative and decreasing. Negative and decreasing. The negative and decreasing section for this polar graph does not come next. It comes here. This is where the graph is negative and decreasing, because it's from 7 pi over 6 to 3 pi over 2. The next color scheme I have here is going to be positive and decreasing. In my rectangular graph, that's a really large section from pi over 2, that's the positive y-axis, all the way to 7 pi over 6, which means it's actually this entire section going past the x-axis and underneath a little bit. The last one, where it says that it is negative and increasing, we said this is from 3 pi over 2 to 11 pi over 6, which is going to be this piece right here. So we have one little tail left that we didn't highlight on the polar function. What color do you think that's going to be? Which one of these had like two little bitty sections? They're red. So this section right here is also positive and increasing. In my opinion, it's really hard to see this on a polar function. It's much easier to understand these concepts on a rectangular function. So we're going to be graphing all of the polar functions rectangularly today, which is why I had you review it before we started the notes, so that we can see what's happening in something that's a little more clear for us on whether it's getting positive or negative, increasing or decreasing. Now what this means for us today in our conclusions is not just highlighting graphs, is actually discussing the distance between the function and the origin. For the red and the purple, the distance between the function and the origin is increasing, which means that it's getting further away. And if you look at our graph here, that kind of makes sense, because for both the red and the purple, if we follow this loop around, my radius is getting further away from the origin itself. So we're going away from it, away from it, away from it, towards it, towards it, towards it, away, and towards again, the origin. So for the blue and the green, the distance is decreasing, which means that we are getting closer to the origin. And that's the sort of questions that I'm going to want you to be able to answer today, is whether the function is getting further away from the origin or closer to the origin, to decide if the polar function is increasing or decreasing. But like I said, it's much easier to do this if you think about this rectangularly instead of polar, since we're more comfortable in a rectangular coordinate plane. This table down here at the bottom just kind of puts this together, reattaching the polar function to the rectangular one. So we'll just use our highlighting again. Positive and increasing was my red color. So it's just taking the interval from your table, attaching the words to it again, and reminding you that that means that it is increasing. The distance between the function and the origin is increasing, just like the radius and the origin is increasing. Then we have positive and decreasing, which was my bluish color. That means we are getting closer to the origin in the blue section, or getting closer to the midline. We have negative and decreasing. That's my purple section next. We are getting further from the midline, or further from the axis. Oh my gosh, the x-axis. We're getting further from it. Then it turns green and we're getting closer to it again. So negative and increasing means that we're getting closer to the origin, or to the midline. And then once we hit that red part again, it's positive and increasing one more time, which means we are getting further away from the midline. So again, the origin you can think of as the x-axis, not the midline, sorry. We're getting further from the x-axis, closer to the x-axis, further from the x-axis, closer, and then further again. Bless you. So a good question you can ask is, well, what do questions in this topic even look like? So the rest of this little section of the notes has 2 examples for us to do to see the kinds of questions that the AP test has asked, so we can use our skills to be able to answer them. On the back, these notes even remind you again, AP exam tip, it is often helpful to sketch the graph of a given function in rectangular when attempting to describe the behavior of a polar function. We're just more comfortable rectangular because we've done that for a lot longer than we've worked with polar. So we reviewed this before we started class, but just because I don't think we wrote it down. A typical positive sine function, what does it look like? It starts at the what? Origin. It goes up, down, up in 2 pi. That's a positive sine function. What does a typical cosine function look like? Where does a cosine function start? At a max, and then it goes down to a min and back up to a max in 2 pi. And what does the A, I just said the answer out loud. What does the A change? The amplitude. So the number in front of sine or cosine changes the amplitude. If it's negative, that means it's a reflection over the x-axis. So instead of starting going up for sine, you start going down. And instead of starting up for cosine, you start at a minimum. The period is changed using which letter? B, and the B is inside of sine or cosine. So it will typically show up inside a set of parentheses next to theta. There won't be any phase shifts for polar functions because it doesn't change anything. You would still repeat the same shape over and over again. So we'll just skip C, but what does D change? The midline. So when we're graphing these functions rectangularly, we're going to make sure we remember this so we know how to get a function to make sense. So in example 2, it says, consider the graph of the polar function r equal to f of theta, where f of theta is equal to 2 minus 4 cosine theta. This is what we're going to have to graph to be able to answer this question. Which of the following statements is true about the distance between the point with polar coordinates f of theta, comma theta, and the origin? So we're answering a question using the vocabulary from the front of the page. Let's start by just graphing this function plainly on a rectangular coordinate grid. Is there a change to the midline of this graph? Remember, we are plotting this time y equals, or f of x equals, to negative 2 minus 4 cosine of x. Is there a change to the midline? Yes, it should go up to 2. So I have a midline at 2. So here's 1, here's my second tick mark, here's going to be my midline. Is there a change to the amplitude? Yes, the amplitude is going to be negative 4, which means we need to go up 4 from the midline. 1, 2, 3, 4, and down 1, 2, 3, 4. That's going to be the range of the graph. I've already answered this. What is the period of this function? 2 pi. The b is 1. There's no number there, so that means we can just finish this at 2 pi and call it a day. Now, the trick to this, and we did this in the warm-up, is that you only need to know the tops and the bottoms and the midlines. So halfway between 0 and 2 pi is going to be pi. That's an important point. Halfway between 0 and pi is another important point, pi over 2. What's going to be the tick mark I put between pi and 2 pi? 3 pi over 2. Okay, cool. So let's graph this function. It's cosine, so I'm going to start at a max or min. Do I start at a max or at a min? A minimum. So I'm going to start down here at my minimum. The next tick mark I put is an important tick mark. That's my next center. The next tick mark is going to be a max, and then a min, and then a midline, and then a minimum. If you only label for yourself, because it's not on a coordinate grid, you don't have to count specific boxes. If you only put tick marks for the ones that matter, it's very easy to sketch this graph. Okay, same color scheme as the front. So if you need to flip back and forth to remember what you did. My red was where it is above the x-axis and increasing. There is one section here that is above the x-axis and increasing. It's this section right here. Above the x-axis and increasing. My blue color was for where it's above the x-axis but decreasing, which for my function is going to be all right here. That's above the x-axis but decreasing. My green was where it's below the x-axis and increasing. Oop, that's not even green, which is here. Below the x-axis but increasing. And my purple was where it was below the x-axis and decreasing. Okay, let's read some answer choices here and figure out what's happening. Letter A says the distance is increasing for pi to 5 pi over 3. Well, I know pi. 5 pi over 3 is going to be here, and I'll explain why in a second. But is this section, the distance between the origin and the line, is it increasing? Or am I getting closer as I go through this? I'm getting closer, right? So that's super wrong. We're going to cross that one out. It's definitely not increasing on that interval because that section of the graph, it's getting closer. Between 5 pi over 3 and 2 pi, which is going to be from here to here, is our distance increasing? The distance between the x-axis and my function, is it increasing? They're getting further away. We're going to leave that answer choice. We'll put a little dot next to it. We'll save that one. Maybe a cute little star. Letter C says the distance is decreasing for pi to 5 pi over 3. Okay, well, here's pi. And again, this is 5 pi over 3. Is this distance decreasing? Yeah, I'm getting closer. So we're going to keep that one. Then letter D says the distance is decreasing for 5 pi over 3 to 2 pi. Well, we kind of already answered that. Is 5 pi over 3 to 2 pi, is that distance getting closer? No, the function's getting further from the x-axis. So we're going to cross that one out. I only read the first part of this. I stopped reading at the comma on purpose because the answer needs to work out and the reasoning needs to work out. So let's read the reasoning for part B. It says because f of theta, the function, is negative and increasing on that interval. So from 5 pi over 3 to 2 pi, am I negative? Yes. Am I increasing? No, that function's going down, right? So this is the wrong word to use here. We're going to get rid of that one. Now we're good students, so we're going to verify that C is correct. The reason on C says that for pi to 5 pi over 3, f of theta is positive. Is that true? Is it positive? It's above the x-axis, so yes. And is it decreasing? Yes, so this is the correct answer. Now, a question I expect you to have is, Miss Quigley, how did you know that we were talking about 5 pi over 3 and that was this point right here the whole time? That's a great question, and I don't want you to write this down, I just want you to watch. The reason I know that was 5 pi over 3 is because I was looking for the zeros of this function. So if I solve this function for 0, set it equal to 0, the x-axis, and I solve, I would subtract 2 to both sides. I would divide by -4. And then I would know that cosine of theta is equal to 1/2 at pi over 3, and in the fourth quadrant at 5 pi over 3. There's where 5 pi over 3 came from. It's the place where this actually crosses the x-axis. I have not seen a question that kind of throws that part in there where you have to know that value is different. They're wanting to know if you understand these vocabulary words of increasing, decreasing. So I can tell you in a pinch, you can assume that the numbers in the intervals are where it crosses the x-axis. I haven't seen anything that's done anything different than that. But if you were wondering why 5 pi over 3, that's why. Okay. In example 3, it says the graph of f of x equal to 3 times the sine of 2x, where 0 is less than or equal to x, which is less than or equal to 3 pi over 2, is shown above in a rectangular coordinate system. If the polar function r equal to f of theta, where f of theta is 3 sine of 2 theta, is graphed in a polar coordinate system between 0 and 3 pi over 2, on which of the following intervals is the distance between the point with the polar coordinates f of theta, comma theta, and the origin decreasing? What do you notice about these two functions right here? You notice anything about them? They're the same, right? One is rectangular, one is polar, which means we can use the graph they gave us, we don't have to plot it this time, to answer the questions. So again, I'm going to use the same coloring system. My red was where the function is positive but getting bigger, so going up. So I have this section that's positive, that means it's above the x-axis and going up. And then I repeat that section right here. And my pen just malfunctioned. My blue color was where it's positive but going down. So there's two sections where it's positive above the x-axis but going down. My green color was where it was negative but going up. So underneath the x-axis but increasing. And then my purple was where it's negative but decreasing. This one does end up kind of looking like concavity, and the way we talked about concavity, because the midline is at x-axis, it does match that, but when we shift it up and down, it's different than concavity. So the question here is we're trying to figure out when is the distance between the origin decreasing. So we need to look at these different intervals. For interval letter A, between 0 and pi over 4. 0 and pi over 4. That means I'm looking between 0 and pi over 4. Is this section, is the distance between the midline and the function getting smaller? Is it decreasing? Are they getting closer together? No, they're getting further apart. That's wrong. Between pi over 2 and 3 pi over 4, so pi over 2 and 3 pi over 4, is this distance between the midline and the function getting closer? No, it's getting further away because that graph is going away from, so the distance is increasing. Letter C says to look between 3 pi over 4 and pi. Is this section decreasing? Are we getting closer? Yes, looks pretty good. We're going to hang on to it, but we're good students, so we eliminate all answer choices. Letter D says to look between pi and 5 pi over 4. Is this section getting closer together? No, it's going away from the midline, so we can get rid of that one. C is the correct answer. This is what we did in this problem. Oh, no. It didn't stick. This is what we did in this problem, but we had to do the graph in this problem. which makes it a little bit harder. But that's all we did here is we said, okay, I need to look at it rectangularly so I know whether the graph is going away from the midline or going towards the midline. We just had to graph it for ourselves here. So we've got our first way to describe graphs, whether the radius is increasing, the distance between the radius and origin is increasing or decreasing. Another way we can describe polar functions is talking about their relative extrema. When we talked about relative extrema for other functions, we were talking about maxes and mins. So on a typical sine function, you had a max and you had a min. In the same way, you can talk about this for polar functions. But on a polar graph, a maximum or a minimum is going to occur when the function changes from increasing to decreasing. Not from positive to negative, but from increasing to decreasing, which means that we are looking for points that are relatively closest or furthest from the origin. Now again, looking at a polar function for this is confusing because of their circular nature. So it's a little bit easier to take all of these functions and make them into rectangular so that we can look at it. That's what we're going to do on these problems. So example 4 says, consider the graph of the polar function r equal to f of theta, where f of theta is 1 minus 2 sine of 2 theta. Which of the following statements is true about the graph of this function? Now, before I do anything, I want to see what the rectangular version of this function looks like. So let's graph it. You've actually already done this one. This is one of the ones I had you do maybe at the beginning of class. This one has a midline at 1. It has an amplitude of 2, and it has been reflected. It also has a period of pi instead of 2 pi, because I would do 2 pi divided by the 2 that's inside, which means I don't put 2 pi here at the end. I just want one period of it, so I just put pi at the end. What should I label this halfway tick mark? Pi over 2. What should I label this halfway tick mark? Pi over 4. And then don't make this too hard. If this is 1 pi over 4, this is 2 pi over 4. What's the other one? 3 pi over 4. Okay. This is a sine function, which means it starts at a midline, but it has been reflected because of that negative 2 in front of it, which means instead of going up, I'm going to go down and then back up and then back down again. So here's what this sine function kind of looks like. Based on this rectangular version, we are going to have some sort of minimum here-ish and some sort of maximum here-ish, right? Minimum, maximum. Your polar function would have a minimum and maximum at the same place at the same angle, I guess I should say, at the same angle. So let's see what the answer choices say here. It says the graph of r equal to f of theta has a relative minimum on the interval from pi over 3 to 2 pi over 3. Well, we need to figure out where those values are. Is pi over 3 bigger or smaller than pi over 4? Bigger, which means it would be like here. Is our minimum on the rectangular graph between pi over 3 and 2 pi over 3, which is here-ish? Isn't our minimum back? Okay, so we have to eliminate that one because it's not even the correct interval, because pi over 3 is bigger. Letter B says the graph of r equal to f of theta has a relative minimum on the interval from 2 pi over 3 to pi. Okay, well, pi is all the way over here. Pi over 3 is here, which means if we double it, ends up being here. Do I have a minimum within here-ish to here-ish? No, I had a maximum, right? So I'm going to get rid of this one because this is the wrong word. Which kind of gives you a hint on which answer choice we're looking for. Letter C says the graph of r equal to f of theta has a relative maximum on the interval from pi over 3 to 2 pi over 3, which we said was from here-ish to here-ish. Is that true? No, not even the right interval. And then D, it has a relative maximum on that second interval, which is what we said we wanted out of B. So D is correct. Translating all of these polar functions to rectangular gives you an easy way to answer the questions. And then everybody's favorite, the formula I've asked you to memorize over and over again, average rate of change. In previous units, we learned about the average rate of change. It's just a way to describe between two different points on a graph. We've done this with only rectangular functions. We did it with logarithms, with exponentials. We've done it with, you name it, we've done average rate of change. We can also do the average rate of change with polar functions. The formula stays the same. If you notice, I know that the one I wanted you to memorize, I said y2 and y1, but instead this function is using b and a, but that's just the first interval and the second interval, the beginning and end. It's the same formula I had you memorize. We are going to use this formula to find the average rate of change of a polar function. Geometrically or visually, what this means is the average rate of change indicates the rate at which the radius is changing per radian. Here's what it looks like. Consider the graph of the polar function r equal to f of theta, where f of theta is equal to 3 minus 3 cosine of theta in the polar coordinate system. What is the average rate of change of r equal to f of theta over the interval from pi over 2 to pi? These are the numbers that you're using as y1 and y2, or as a and b. So if we find the average rate of change using my formula, you always start by writing down this as a formula. You would say f of the second interval. So what's the second number, the ending interval? Pi, minus f of the first interval, y1, which is pi over 2. In this case, instead of y1, I guess I should be saying theta 1, theta 2. You get it. Over the second ending place minus the first ending place. Function notation has always meant just plug the numbers in. So that's what we're going to do. We're going to take the function f of theta, this guy right here, and we're going to plug these numbers in. So we'll do 3 minus 3 times the cosine of pi minus 3 minus 3 times the cosine of pi over 2. I'm putting these in parentheses on purpose because we're subtracting the entire expression. I don't want to not distribute that negative sign. Then we'll do pi minus 2, pi over 2. We can't do that math in our head unless they have a common denominator. So I'm going to write pi as 2 pi over 2 minus pi over 2 so that they have a common denominator. If I start evaluating this, the top will have 3 minus 3 times the cosine of pi. What is the cosine of pi? Think about your unit circle. Where is pi? Should be a part of the flat line, right? I guess this way for you. What's the x-coordinate there? Negative 1, but yes, because it's on the negative side. Okay, and then I'm going to subtract 3 and make sure I distribute that negative sign so that it's plus 3 times the cosine of pi over 2. What is the cosine of pi over 2? Zero. In the denominator, I have 2 pi over 2 minus pi over 2, which means I'm just left with a single pi over 2. Arithmetic time. I notice immediately that I have a positive 3 and a negative 3. They cancel. What's 3 times 0? 0. So essentially like that cancels out as well. Which means I just have to do negative 3 times negative 1, which is what? 3. So I have 3 over pi over 2. To divide fractions, the rule is keep, change, flip. Keep the same numerator on top. If that's a fraction, leave it as a fraction. Then you multiply tops times tops, bottom times bottoms. This is 6 over pi. That is the average rate of change between pi over 2 and pi for that function. Now you're on the next question that we do this, you're going to do this process like 4 times. Ask me some questions now before I let you try the next one. Okay. Example 6. It says the figure shows the graph of polar function r equal to f of theta, where f of theta is 3 times sine of 2 theta between 0 and 2 pi in the polar coordinate system. On which of the following intervals is the average rate of change of f of 0 equal to 0? So what I need us to do on this problem is do that average rate of change formula that we just did in the problem before this for each of these answer choices. I will do A, y'all will do B, C, and D. I'll tell you right now, even when I did this, I ended up running out of space. So try to aim to get A, B, and C in the top section, and then you won't need a ton of space for this guy, so you can jump down to the bottom to do D. I just didn't leave you enough space. Here's what this looks like. If we're finding the first average rate of change, so the average rate of change for answer choice A, we are doing f of 3 pi over 4 minus f of pi over 4. Where did I get those numbers from? The ones I plugged in. The answers. I make sure I put the bigger one first and the smaller one second. Then in the denominator, you just take those same numbers again. Voila. That's the showing my work part, and now I'm ready to do some math. We actually substitute those values into the function itself. So this will end up being 3 times the sine of 2 times 3 pi over 4. What's 2 times 3? 6. What's 6 divided by 4? It's still a fraction. This ends up being 3 pi over 2 because 6 over 4 reduces to 3 over 2. I'm trying to save you some space and do at least that little part together. So I multiplied 2 times this angle. Then I do that same thing over here. I'm going to do 3 times the sine of 2 times pi over 4. What does 2 times pi over 4 become? Pi over 2. In the bottom, I have 3 pi over 4 minus 1 pi over 4, which is 2 pi over 4. What is the sine of 3 pi over 2? Oh gosh, guys, we got to get that unit circle. These are all non-calculator portions of this test. That's -1 minus 3 times the sine of 1/2. The sine of 1/2 is 1 all over pi over 2. Three times -1 is -3 minus 3 times 1, which is 3. Just to save myself room, we can do this part at the same time. What is 3 minus 3? -6. If we keep change flip, keep the top, change the bottom, keep change flip, ends up making this to -12 over pi. Is that 0? No, we're looking for which one of these has an average rate of change that is equal to 0. We got this one to be equal to -12 over pi, which is not what I wanted. I need you to try doing the average rate of change formula for answer choices B, C, and D. Like I said, you'll probably run out of room here. We need a little bit of space on the bottom, but not all that much. So you can use some of that extra space down there at the bottom. Okay, obviously that's a lot of arithmetic. If you got at least through one of the answer choices, check which answer choice you did. See if you followed along with me. And maybe snap a quick picture so we don't have to stick here for a minute. Obviously, I upload my notes to Google Classroom, but you know the drill. So we wanted to answer which of the following intervals is the average rate of change equal to 0. So which answer choice should I pick?
C.
C. Now that was a lot of work, and I understand that. If I was taking an AP test and I stumbled upon a question like this, knowing how long this is going to take, this is the last question I do in that section. I'm going to go answer the rest of them, and if I have time to come back to do all of this arithmetic, I will. Yeah? But if they don't give you the equation, like in number 7, number 7 requires us to attack the problem a little bit differently. But if we remember that average rate of change is like slope, we may be able to answer this question pretty quickly. It says, in the polar coordinate system, the graph of a polar function r equal to f of theta is shown with a domain of all real values of theta for 0 between 0 and 2 pi. On this interval of theta, the graph has no holes, passes through each point exactly one time, and as theta increases, the graph passes through the labeled points A, B, C, and D in that order. Let's make sure we actually see those, because sometimes it's hard to see. Here's A, here's B, here's C, here's D. It says it goes in that order, which makes sense, because we know these graphs circle this way, so it has to do like a cute little cardioid heart thing. On which of the following intervals is the average rate of change of r with respect to theta the least? We weren't given an equation here, so there's going to be no plugging in values. But what we will do is look at the coordinate points it gave us and see what's happening for each of those coordinates. So using your skills from plotting points on a polar coordinate, what is the coordinate of point A? What is the radius there? It's what you think it is. I know it's not on a corner piece, but what's between 2 and 4? 3. It is 3. What's the angle? 0. Okay, cool. We moved no way around the circle, so it's angle 0. Now what about B? Not using negative because we're still following the same circle. So I want you to give me a positive radius and then an angle. 3, and then what angle would arrive me there?
180.
Which in radians is pi. So yes, 180, but in radians is pi. What is the coordinate point for C? This one we have to get a little bit estimaty, I feel. But if I look at where C is and I kind of travel that same circle all the way around, what would you approximate that value to be? 5-ish. I'm going to specifically put 5.5 because to me it looks a little bit further than halfway, but 5 would be fine as well. We're just estimating here. What is that angle? If we count the little sections, there are from 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 of these little tick marks, for lack of a better word, all the way around. But what am I counting by? 15 over what? How many of those tick marks are there in the top 2 quadrants? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12. So it's 15 divided by 12, which if you reduce 15 divided by 12, that's 5 pi divided by 4. Now what about D? What would you estimate for that one? I agree. Whatever you said for C, the same, 5.5 looks in the same ring, same area. And what's the degree on, not degree, what is the angle in radians on that one?
7 pi.
I agree, 7 pi over 4. Because from 15 we add 16, 17, 18, 19, 20, 21. 21 over 12 would reduce to 7 pi over 4. Okay, we want to know the average rate of change of r with respect to theta, which one is the least? From A to B, did the radius change? No. So from A to B, we went from 3 to 3, which means we have a rate of change of 0. We didn't change at all. From B to C, we went from 3 to 5.5, which means we increased a little bit. We're just going to put a plus sign for increase. From C to D, I went from the radius of 5.5 to a radius of 5.5. What would be the average rate of change there? 0. From D to A, I went from 5.5 to 3. What do you think I should put there? A negative. Remember, this question is asking you on the following intervals, which is the least? What's going to be the smallest number up there? The negative. This is the correct answer. Because it's the least change we would have. Putting this all together, and I can imagine an FRQ potentially using something like this. Maybe not with polar, but definitely the idea of estimating using the average rate of change is part of an FRQ. But if we look at the last question here, it asks us to use the average rate of change to estimate values for my function. Okay? If you recall from Algebra 1, we have a point slope form of a line. I want you to highlight this in your regular highlight color. Okay, y minus y1 equal to m times x minus x1, where you just need a coordinate point and a slope to plug stuff in. You still just need one point and one slope, even in polar, to estimate using the average rate of change. It's the same for any kind of function. If you have 1 point and an average rate of change, you can use this idea in any type of function. Okay? If we rewrite this function that we just highlighted in yellow so that y is by itself, that means I would add y1 to both sides. So the formula actually ends up looking like this, which is the more helpful version for us to estimate an answer. But if you notice, in this version we just wrote down, you have a slope in front of a set of parentheses. But slope is really just the average rate of change. So if you notice, I have an average rate of change right in front of a set of parentheses in the polar version. Then you just need one input-output pair of an input value x and an output value y. So you have the same thing in a polar function, an input value theta and an output value f of theta. That would be a radius. F of theta. So we can use this same concept of point slope form. Your point is a point, coordinate point's the same thing, but your slope is the average rate of change. So we can use that to predict some value for the function. So we're using that f of theta is approximately equal to formula down here. It says the table above gives the values of a polar function f of theta at selected values of theta. Use the average rate of change of r equal to f of theta over the interval from pi over 6 to 7 pi over 6 to approximate f of 5 pi over 6. That's a lot. These are going to be used for average rate of change because we want to know the average rate of change in that interval. That's going to be used just like we did for average rate of change a second ago. This is going to be the function we are looking for. This is like your x, or this is like the theta that we care about. All we need is a coordinate point, which we can get out of the table, theta, comma, f of theta, to fill in this formula. If we are finding f of 5 pi over 6, that will end up being approximately equal to, and again, I'm using the formula from above, f of one of the angles. I don't care which one we use. Would y'all like to use this angle or this angle? I agree it's smaller. We're going to use pi over 6. That's a strong choice. Pick the smaller angle. Plus the average rate of change here, which we are going to find to be f of the bigger interval number, not a 2, that's a 6, minus f of the smaller interval, all over the larger interval minus the smaller interval, endpoint, multiplied by theta, 5 pi over 6, minus the same number you chose, pi over 6. Let's make this make sense. This right here is the average rate of change. All I did was use the numbers from the interval given in the problem. Check. Do we see at least that part? The other thing I used was a coordinate point, pi over 6, comma, f of pi over 6. That's my x1 and my y1, my theta 1 and my f of theta 1. The last thing I did here is because there is a 5 pi over 6 here, I have to put that same number here. That's what I'm estimating for the future, which is why that number goes there. Let's start filling some stuff in. Based on the table, what is f of pi over 6? 2. Based on the table, what is f of 7 pi over 6? Based on the table, what is f of pi over 6? And then I can do 7 pi over 6 minus pi over 6. That ends up being 6 pi over 6. I'm going to multiply that by, what is 5 pi over 6 minus 1 pi over 6? 4 pi over 6. Start reducing where we can. 2 stays the same. I can do some stuff on the numerator here. -1 minus 2 is -3. These 6's are going to end up canceling out. So I end up with just pi in the denominator. And I'm multiplying that by 4 pi over 6. Let's go ahead and reduce that number, actually. 4 pi over 6, we can reduce that fraction. What does 4 pi over 6 become? 2 pi over 3. My spidey senses are going crazy about that multiplication problem. What can you cancel? The 3's. What else? The pi's. So that number ends up just being -2. Well, 2, but then there's a negative in front, so -2. So you have 2 plus -2, which is what? 0. Our prediction for 5 pi over 6, based on the average rate of change, is 0. Now, this may or may not be accurate. And part of one of the questions in one of the FRQs, which we will work on the FRQs when we get into review, is knowing whether your model, our answer, is accurate enough to use. Okay, we don't have enough information in this question to know that, but we will eventually be able to answer questions of whether our predictions using average rate of change are good enough for the function. Okay, I know that this was really long, and y'all just listened to me talk for a really, really long time. Okay, and again, your homework for today is not practice problems, but is to go listen to somebody else explain this, just in case what he says is better than what I say. So in AP Classroom, that's going to be your homework assignment. For the rest of this class, if you want to just go back over these notes before you leave and see if there's a point you want to ask me anything where you got lost or where I went too fast, I think that's a good use of time because you don't really have enough time to start the AP videos, especially because you know AP Classroom takes forever to log in. But that is your homework for next time, is to come back with those videos watched so you can hear another person explain this topic to you. Oop, I left this on the whole time.